Well, this is Lean Together 2025. This is our last talk of the conference, and I'd like to welcome Yuma Mizuno to give us a talk on metaprogramming on monoidal categories.
Thank you for introduction. So in this talk, I would like to share my experience writing metaprogramming code for monoidal categories. So I will talk about two tools. The first is coherence tactics, so which automates the coherence conditions for monoidal categories. And the second is string diagram widget, so for visualizing the morphism in monoidal categories. So coherence tactic. So first, I'd like to explain how metaprogramming appears in when we consider some algebraic structure. So this is a simple example. So how to prove such an equation in Lean? So one answer is simp only malazos 1 mal 1. So this always works. So this is because we have some kind of a meta theorem that says that any such equation can be simplified to normalized form by iterated application of the associative law and unit laws. So this is a meta theorem meaning we do not need to formalize this statement in Lean to prove actual identities like this. Rather, it ensures that just simple works. So, okay. And so if we have some general tactic and it works, it's completely fine. But in other situations, we often need some specialized tactics like ring or arbel. And the coherence tactic is another example. So this proves coherence conditions in monoidal categories. So in that case, we also need some specialized tactic. So now I would like to explain what monoidal categories are and coherent conditions are. So this is a definition of monoidal categories. A monoidal category consists of the following data. So the definition is similar to the monoid definition of monoid, but in monoid, underlying object is set, but in monoidal categories, the underlying object is a category. And multiplication is now a functor, which is called tensor product and denoted by this symbol. And we also have unit element, which is an object in category. And in monoid, we have associative law and unit laws, but they are now isomorphisms. They are isomorphisms, so called associators and left and right uniters. So these are isomorphism between object in the monoidal category. And we also need to assume that these isomorphisms are natural with respect to objects, but I'm omitting these conditions here for simplicity. And we also need coherence conditions. So this is a completely new condition that is not existing in monoid. So coherence conditions are conditions on associators and uniters. So, I should. Okay. So for example, we can define isomorphisms between these two objects by composing associators and uniters in appropriate way. But actually, there are several ways to do so. So we can have multiple ways to define isomorphism between these two objects. Coherence condition states that they are all equal. So we need to impose coherence condition in the definition of monoidal categories. But the problem is, yes, there are infinitely many coherence conditions, and we cannot write the infinitely many condition directly in the definition in Lean. So structure command cannot allow us to write some infinitely many conditions. But there is nice things. called coherence theorem. So coherence theorem says that all coherence conditions follow from just two conditions, special conditions called pentagon identities and triangle identities. So pentagon identity is some associative coherence conditions for four objects, and triangle identities is a coherence condition with a middle unit element. So in the definition of monoidal categories, we only need to assume these two conditions, so rather than assuming infinitely many conditions. So this is the coherence conditions in monoidal categories. So, but then, so how to prove coherence conditions in ring? So actually, so we will encounter many coherence conditions when we work on monoidal categories formalization. So how to prove that? Actually, we need some tactic to do that. So because coherence condition is some kind of meta theorem, it is theorem about expression. So we need some tactic. And actually, there are two ways to implement the coherence tactic. So the first method is transporting an equation from a formalized coherence theorem, which is a theorem about free monoidal categories. Actually, this is already massive. So we can write some metaprogram to transport the equation. And the second method is so writing some direct proof producing tactic, manipulating ring explicit terms directly. And both work, so completely fine. But experience has shown that the transporting tactic, at least without some optimization error effort, relies on some heavy definitional equalities and is very slow when expressions are long. On the other hand, the proof producing tactic works well in practice. And Mastery previously used the first method, but recently switched to the second one. And I'd like to do some demo. So can you see the VS Code? So this is a example of the coherence conditions. So we have two morphisms here, and these morphisms are left uniter and right uniter on unit object, and both have the type 1 tensor 1 to 1. So coherence condition, by the coherence condition, so this should be equal. But actually, proving this equality from the pentagon identities and triangle identities, some puzzle and not completely obvious. And so the coherence tactic is very helpful in that case. And the coherence tactic is available in Massive as a monoidal tactic. So we can use this monoidal tactic to prove the goal. And actually, this is a proof producing tactic. And we can see the proof steps by setting, so set option trace.monoidal true. So then we can see, so how to prove this, these identities. And so this is a simple case, but this also works for more general, more difficult case. So this monoidal tactic solves this goal. So you can think, you may think that so this is some artificial example, artificially complicated example, but actually this appears in some working example. So we need to prove such equation when we work on some monoidal categories. So we really need a tactic to prove such identities. Okay. And I'd like to talk about some implementation details. So when manipulating ring expressions, So it is useful to define special expression types. So for example, this object type is for object for monoidal categories and expressions for object of monoidal categories. And this ISO is expression types for isomorphisms. And yes, one remark is that we do not use dependent type here. So isomorphisms is in formalized setting, isomorphism of category is dependent type. So it depends on domain and codomain. But here, so we define the expression type. So I didn't use dependent type because yes, dependent type is more trickier than non-dependent type. And so I will not talk about the detail of the implementation, but here is some, so my experience. So here is a part of the code producing some linear expressions. So the first is monads are always useful. So we can use do notations, and so we can set some global environment like monoidal category instance. So we should remember the monoidal category instance. And second, so QQ is useful when constructing linear expert terms. So in this code, so XE and YE are actually linear expression terms. And we need to construct the tensor product of these expression. But it is usually annoying to do so. But if you use Q macro, so then you can simply define the tensor product expression just as we do in the usual formalized math. So we can use tensor notation here. So it is very useful. And finally, and we can construct some linear expression term by meta-m functions like since instance or mkapp function. But they are not sufficiently fast for our purpose because so we need to construct so many expressions. So I didn't use that. So here are some my experiences. Okay. String diagram widget. So first, I like to recall some two categorical point of view of monoidal categories. So monoidal category can be thought of as a one object, two category or bicategory, just as monoid can be thought of as one object, usual category. And so they have some graphical description. So zero category is a set which can be described by a collection of points. And one category is a usual category, and we have arrows between points. So they are morphisms between objects. And in two categories, we have arrows between arrows. So they are represented by two cells like this. So they are triangle or sometimes square or pentagons. So we have such graphical description for bicategories and monoidal categories in special case. And string diagrams are another visualization. So they are dual of the two cell diagrams. So dual means that so each two cells is a node in the string diagram, and we connect two nodes if they share some edges in the original diagram. So this is a string diagram. And string diagram widget is a tool to show this diagram in the right window of the editor from the expression, linear expression. So here is a demo. So for example, so this defines some morphism in monoidal categories. And Yes, and easiest way to use string diagram widget is string diagram command, and you can put some morphism here to see the string diagram associated with these morphisms. So this is morphisms in my slide, and you can also see the equations, and this is actually one working example. So this is one axiom in the monoidal categories. So even you don't know what is monoid in monoidal categories, but if you can see this diagram, so this you understand. So this also says some kind of the associativity of multiplication. So it is very nice. And this is nice. And actually, string diagrams widgets are more useful when you want to write a proof. So this is another example. So this is a more complicated example, and I will not explain the detail. But this is some theorems about bicategories, adjunction, and mates of bicategories. And this is actually appearing in the Emily Reed's talk in the first day of this conference. So in that talk, some two categorical theorem is described by pasting diagram, but so here we can see the corresponding string diagrams. So this theorem says that some left diagram is equal to this right diagram. And actually, so you can see these diagram to, so how to prove this identity. Actually, so in adjunction, there is an identity says that unit counit is cancelled to the identity. And so here, so we have unit and counit. So we can cancel these two morphisms to get this right diagram. But this is not all the contents. We need to, so this adjoint counit is not right after the adjoint unit. So we need to swap the order of the morphisms. And this is done by this whisker exchange theorem. So this always true for any bicategories. So we can always swap the composition order of the two morphisms. So what we need here is, so first step should swap this adjoint 1 counit and this adjoint 3 counit. We need to swap these two things. And so when writing the proof, this diagram it's so helpful to see what is the next step. So we know that next step is swapping these two. Oh, some weird things happen here. Okay. So what we need to do is in the editor, so we need to write the expression. This is not automated at this moment, so we need to write something in the left window. But what we need is put parentheses around these two things. So here we need to put parentheses, and we need to, so this composition are type correct composition. That means codomain of this coincide with the domain of this morphism definitionally. So that means, so this adjoint 3 unit is nothing to strands, but it is actually identity to the composition of two one morphisms. So we need to insert this identity by hand. So like this. But this is all we need. So after we have some type correct composition here, we can use this rewrite tactic to exchange these two nodes. And actually there is one more thing. So these two string diagrams are the same, but this is not no goal. So we should prove something. And this is because in string diagrams, so associators and unitars are omitted. But in the actual linear expressions, there are some associators and unitars in each composition step. And so, and the left-hand side diagram and right-hand side diagram possibly have different associators and unitars. So to prove this, so we need to use coherence conditions. So the coherence tactic work here. So bicategory version of coherence tactic is available by bicategories. So it proves the goal here. So what we need is iterate this step. So we swap the diagram again and again and again. And finally, we obtain this diagram. And we can use unit point cancellation here to get this right diagram. So this is yes, how to use a string diagram as well as coherence tactic. Okay. And this is some implementation details. So there are, yes, some normalization procedure in the backend. So that means, so extracting atomic two morphisms and removing associators in unitars. So this is some backend procedure, and drawing is by proof widget with its Pendle support. So Pendle is a software for drawing diagrams by specifying constraints. So this is a rough explanation, but so there is a remark. So actually, so we have the monoidal tactic and bicategory tactics, but actually they are general purpose tactics for proving equations involving two morphisms. So other than just associators and unitars. So actually, so they solve any equation such that the left-hand side diagram and right-hand side diagram have the same string diagram. So we implicitly use coherence conditions by coherence tactics. And they also have some normalization procedure for two morphisms. And actually, the normalization is not for drawing string diagram, but normalization is essentially the essential part of these tactics. So in other words, we don't need too much effort to extract some data for proving string diagrams. Almost all things are already done in coherence tactic. Okay, this is a remark. And future direction. So yeah, I'd love to discuss these topics with anyone interested. So first is more general purpose tactic, which involves the whisker exchange relation. So in the example, so I need to write many whisker exchange relations in calc step. So it will be nice to have general purpose tactics that automates that part as well. And the second is coherence tactics for symmetric monoidal categories or possibly braided monoidal categories. And I think the first step might be some yes, meta version of the word problem. So bring word problem for symmetric group and braided group. And the third is string diagrams to code program. So string diagram widget is code to string diagram program, but yeah, it would be nice to have opposite one. And the final one is drawing pasting diagrams. So string diagrams are nice, but yes, sometimes pasting diagrams are more intuitive, especially in category theory. So it's nice to have this feature as well. Okay, this is the end of my talk. Thank you for listening.